It's time to talk about the wonderful world of color. Actually is a pretty cool world, I guess. But as it relates, of course, to Adobe Illustrator Creative Cloud. That's why we are here. Now, don't forget, technical information, especially in this case, is about to be disseminated, so please stay alert at all times. Let's get started by talking about, just in a nutshell, what do we have? What's available? If you go into Adobe Illustrator and start working on a document, you have two color spaces. The first one, of course, is RGB, additive. That means red, green, and blue colors. The second one, of course, is CMYK, subtractive, cyan, magenta, yellow, and black. Now, these represent primary colors. All the visible colors are derived from these prime colors, every single one of them. And in Adobe Illustrator, you have, well, about 16.7 million colors. Now, that can vary. It can go up and down, but that's the average image in Adobe Illustrator. What we're talking about now is a little bit on intent. Now, what is my intent for my image? And that's very important to understand. Stephen Covey had an expression, begin with the end in mind. And we should do that in Adobe Illustrator before we start on something, because it can cause problems down the road if we're not in the right color space. So, usage, for example, for RGB color space, the world of light. Okay, I call that the world of light. Number one, monitors, television sets, mobile devices, things like that. We are painting with light when we work in RGB. Now, the opposite of that, and it literally is the opposite, is CMYK color. Color space, I call it the world of absorption. Some people call it the world of inks, and that's true. But everything in the world that's not on a monitor out there reflects color, okay, or actually reflects light waves. And the color that gets to our eyes is based on what we see. So we're talking print in our world. Print and maybe paper, which are about the same thing, I would think. And the colors are cyan, magenta, and yellow. Now, technically speaking, if you could take 100% of cyan, magenta, and yellow and mix them together, it would produce a black. But because of impurities in inks and things like that, they add that fourth can of paint, if you will, CMYK, and the K stands, of course, for black. All spaces have a color gamut. Now, think of it this way. I have wide gamut RGB up there, sRGB and CMYK, and notice how they get smaller and smaller, and the CMYK one right here is actually quite small. Now, why is that? Well, when you're working in the world of color, and you're working subtractively, and that's CMYK, CMYK doesn't have the saturation capability of colors on a monitor. So what you need to realize when you're working, based on your intent, is that you might be seeing something on your monitor that might not actually be produced when you print. We'll talk about how you get around that. But everything has a gamut. I have an HP printer. I have a Canon printer. They have a different color range. If I had a $10 million Heidelberg press, it would have a different color range. A television has a different color range. A monitor has a different color range. The best thing to do in that situation when you're working is, of course, testing and checking things out. But let's talk just a little bit about subtractive color. It's just something I think that's kind of important to understand how it works. In subtractive color, let's pretend that that gray area down there is a mirror, and it's coated with silver. That is the most reflective metal we have on this planet, silver, and it's usually used to back a mirror. Now let's pretend the glass is perfect. There is no absorption in the glass. So it would, say from sunlight, which is trichromatic colors, red, green, and blue, it would reflect everything that hit it. If you get into something like maybe something a little bit grayer, say for example, as it gets darker, that's not a mirror anymore. Now, see, I don't like to use the word darken or darker. It's got more absorption qualities. So you begin absorbing through the material some of the colors. They start going down and absorb into that, well, whatever it is, and then what's left is reflected back up. And we could keep this up all day long, but if you get into a pure black body, and actually one of the most efficient absorption materials in the world is actually black velvet. It will absorb the color and reflect none of it back theoretically. It all gets absorbed. You take something outside, for example, on a hot sunny day. If it's white and it's black, not only does the black absorb the color, it also absorbs radiant heat and everything else. It's a big sponge, if you will. Now, where does color come from? Because right now my examples are in neutral body colors. For example, if you look at the color red, the reason you see red is because the green and the blue are absorbed by the material. We don't see red. Our mind sees red. What it really looks like, I guess in a sense we have no idea, because we're not really seeing objects. We're seeing the light that's reflecting off of them. And the reason we see color is different material absorbs different parts of the spectrum. I mean, that's kind of what it's all about. So what's the bottom line here? Well, it's kind of anticlimactic compared to what I just talked about. If you're working, say, for example, with an intent of going out to paper, print, etc., then you want CMYK color, which theoretically, when mixed together, produce a black, like in the center. If you are going out to monitors or television sets, Blackberries, iPhones, things like that, then you would stay in the RGB additive, which, since we're working with light, if you shine red, green, and blue totally together, they produce a white. RGB additive and CMYK subtractive are actually the exact opposites of each other on the color spectrum, but it's the intent that will determine which one you use.